All right, so here's a good practice problem for us. We would like to know how many atoms of iron are in 15-gram sample of iron 3 oxide. All right, so there's some fundamental things that you have to remember from previous chapters here. Do you want to lead us through this one, Fred?
Um, okay, so I think you mean like an equal sign?
All right, good. So yeah, we start with an equal sign. All right, what units are we after?
Atoms of iron.
All right, so we want atoms of iron. And then what are we starting with?
15 grams
15 grams of what?
of iron 3 oxide.
Okay, how critical is it that we know what iron 3 oxide means?
I guess it's important.
Yeah, it is, because the number of iron atoms in that compound is going to determine how many atoms there are for every 15 grams of it. So we need to know the chemical formula. What does the 3 mean? Do you remember what the 3 means?
Yeah, that means the charge on the iron.
That's right. So if I have an iron with a +3 charge, right, and then it's combining with oxygen, what does oxygen form?
Oxygen forms a -2.
That's good. Oxygen forms a -2. And let's get our periodic table up here. Now, the location of iron is such that it's a transition metal, so you can't identify what the charge is simply by hearing the name iron oxide. And that's why that iron 3 oxide is important. It helps us know that the iron has a +3 charge, right? Okay, so what ratio are these going to come together in?
2 irons and 3 oxygens.
Okay, so 2 irons, because that's a +6, 3 oxygens, because that's now a -6, right? Okay, good. So Fe2O3, that is our iron 3 oxide. So 15 grams of that, Fe2O3, and then what?
Grams of iron oxide on the bottom.
All right, grams of Fe2O3 here, 2 moles, right?
Yeah.
We always grow land of the moles because this is a molar relationship there. And that allows us to go from moles of Fe2O3 to what?
Moles of iron.
That's right, moles of iron. And I can look down here and see that there's 2 moles of iron for every one of these, right? So there's 2 moles for every one of those. And then I can go from moles of iron to atoms of iron. Okay? Now this is kind of tricky, but we've gotten some practice using Avogadro's number. What do we do here?
A mole is just like a dozen, but not 12. It's 6.02 times 10 to the 23rd.
Good. So there's 6.02 times 10 to the 23rd. Atoms of iron for every mole of iron. All right. So calculator out. We got, let's see, does that help the calculator? Not much. So we got 15 grams. Oh, what's this one?
Oh, that's the molar mass.
Okay, so how do we determine that?
Oh, it's given to us.
Where?
Oh, on the slide.
Oh, there we go, yeah. So 159.7, that'll do as far as significant digits goes. 159.7 for every mole. So 15 divided by 159.7 times 2 times 6.02 times 10 to the 23rd. All right, so 1.13 times 10 to the 23rd should be our answer. Is that one of the answers?
Yeah, that's A.
Okay, good. Great stuff. All right. So, if we're going to determine empirical and molecular formulas, or we can determine empirical and molecular formulas from what we call percent composition. We can also take percent composition and determine empirical and molecular formulas. Now we have to have an understanding of what percent composition means. All right. Some people might look at water and say, oh, there's 3 things here. There's 2 hydrogens and 1 oxygen. And so that means that it's 33% oxygen and 66% hydrogen. And that's true in terms of the number of moles of, or sorry, number of atoms of things, if you want to just do that. But that's not how you quantify how much material there is, because oxygen has a significantly higher mass than atoms of hydrogen, atoms of oxygen do, right? So our percent composition isn't by just the number of things, but it's by the mass of material. So I can look at something like water and say that the molar mass of water is 18 grams for every mole. That's oxygen is 16 on the periodic table. Each hydrogen is 1, so that's a total of 18. And then I can take the contribution by the oxygen, which is 16 grams for every mole of the material. 16 divided by 18 times 100, right? You can get that into a percentage, would be the percent oxygen. Okay, so we've got 89% oxygen in this because there's 16 grams of oxygen for every 18 grams of the water. All right, so oxygens contribute 89%. The rest will be contributed by the hydrogen. All right, so we took the molecular formula, we counted how many hydrogens, and we said that for the percent hydrogen, we would go 2 grams of hydrogen for every mole of material over the 18 grams of water for every mole of material. So then we would do that again, and you could also just take 100 minus the 89, but we'll do this 2 divided by 18, and there's our 11.1%, this is 88.9, and 11.1% hydrogen, okay? So, from our molecular formula, we can identify the mass percentages, right? And if I take the mass percentages, if I say a compound that I'm aware of has 88.9% oxygen and 11.1% hydrogen, I can say, well, that's kind of the same as saying a 100-gram sample has 88.9 grams of oxygen and 11.1 grams of hydrogen. And then I can convert this 88.9 grams of oxygen to moles of oxygen, right? There's 16 grams of oxygen for every 1 mole of oxygen. So I can go 88.9 divided by 16 and say in that 100-gram sample, there's 5.56 moles of oxygen. Do the same thing with the grams of hydrogen, 11.1 grams of hydrogen.
Where did you get that grams from?
Well, if we have a condition, and remember where we got these percentages from?
Yeah, I remember those percentages. But how did you turn them into grams?
Well, we can pretend like if these are the percentages, then I can choose any mass. I could say, okay, if this is the percentages, and here I have a 10-gram sample of this material, whatever it is, right? Then I could take 10 times that percentage, and it would tell me what percentage of the material I have, 10 times that percentage or that fraction, and tell me what mass of the hydrogen I have. If I just say I have a 100-gram sample, then I can pretend like these percentages are just actually masses of those different elements, and then I can identify how many moles that mass represents. See that?
Okay, I think I got it.
Same with the hydrogen. If I have a 100-gram sample and I'm told that these are the percentages of the different components, and that means I have 11.1% hydrogen, 100-gram sample, I can pretend like it's 11.1 grams of hydrogen. And then I can go from grams of hydrogen to moles of hydrogen, and that's the molar mass.
Molar mass is 1?
That's right, 1 gram, 1 mole. So 11.1 grams of hydrogen. Oh, sorry, moles of hydrogen. Okay? So now I have 5.56 moles of hydrogen and 11.1 moles of 5.56 moles of oxygen and 11.1 moles of hydrogen. Okay, and then I can take that molar ratio that I found and say, okay, so my chemical formula now, because that's what molecular formulas are and chemical formulas are, they're molar ratios of material, of atoms, right? So I can say I have some compound has oxygen 5.56 moles, hydrogen 11.1 moles. So that's my formula, my empirical formula. Now it's not a whole number ratio, and I can get a whole number ratio. The easiest way to do that is divide them both by the smallest number, right? And if I take 11.1 and divide it by 5.56, that gives me 1.99, and oxygen, it gives me 1 H2. So there I got back my molecular formula that I started with, right? Started with the molecular formula, identified the mass percentages of the different elements, pretended like I had a 100-gram sample and that was masses of materials instead of percentages, and then I went with those masses of materials and converted those back to moles, and then I can get the empirical formula back. Okay?
So why did we do all that?
Well, it's just to show you that there's this relationship, an important relationship between the percentage, the percent composition, which again is in mass, so mass percent, and the empirical formula. It's important enough that we can identify the empirical formula from the mass percentage. So here's an example. 10-gram sample of a compound contains 2.5 grams hydrogen, 7.5 grams carbon. We can take the mass of the hydrogen over the compound and the carbon over the compound times 100 and get our mass percentages, right? And so can you identify the mass percent of sodium, carbon, and oxygen in this compound? Think you can figure that out, Fred?
Yeah. So that compound is sodium carbonate, right?
That's right. Very good. You don't need the periodic or the polyatomic ion chart anymore?
Well, sometimes I do, but the carbonate one I got okay.
All right, good. So let's keep that nice and handy for those people who aren't quite there yet. So the carbonate, CO3, 2 minus, and sodium, there's 2 sodiums, right?
Yeah. We knew the carbonate was 2 minus because sodium is a +1.
Yeah, that's true. That's true. All right, so sodium carbonate there. What's the molar mass of sodium, or sorry, what's the molar mass, the formula mass of sodium carbonate?
2 23s, 112, and 3 16s.
That's good. 3 oxygens, that's 6 to the 16s, 112, that's the carbon, and then 2 of these sodiums, 23s.
Yeah, okay.
So I'm going to do the easier way, right? Is that okay?
Oh, you mean ask Google?
Yeah. What's the molar mass of sodium carbonate? 106. Oh, is that good?
Yeah, that's okay.
So then what do we do here?
You take the sodium, the mass by the sodium, and that's 2 23s, so that's 46.
So there's 46 grams of sodium here. Is that true?
Yeah.
And there's 106 grams of the what?
Sodium carbonate.
All right. So the 46 divided by the 106 times 100, right? That will be our percent sodium. Is that true?
Yeah.
So again, we got the 46 where?
That's the periodic table, the mass of 2 sodiums.
Very good, 23 and 23. Okay, so 46 divided by 106, so 43.4%. Okay, and how about the carbon?
That's 12 divided by 106.
Okay, so that's 12 divided by the 106. So that's 0.113 or 11.3%. This is 43.4%.
And then the oxygen is 46.
3 oxygens is 46 divided by 106. So that's 43.4% as well.
No, not 46. Did I say 46?
I thought so.
32 plus 16. Is that 46?
Yeah, that's right. 32 plus 16.
No, it's 48.
48. 48 divided by 106. So we're 45.3%. Okay, there we are. That's the percent what?
Sodium.
And this is the percent
Carbon.
carbon percent. And this is the percent oxygen, right?
Yeah.
All right, good. So we can identify our mass percentages pretty straightforward, right? Now the sum of these percentages,
Oh, that's just 100.
that's right, it's always going to be 100. Okay, good. Good stuff.